Okay, good morning. We'll start with the generation of AM signals. So, start with the generation of AM signals. Generation of AM signal. So this is usually a double sideband, okay, full carrier, right? This is double sideband full carrier. So there are usually two methods for the generation of AM signal. First one is square law modulator. Square law modulator. You have a modulator that's called as square law modulator, and this helps in generation of double sideband full carrier. Second one is switching modulator. Switching modulator. So this one and this both helps in the generation of AM signals. So we'll start with the square law modulator. Square law modulator. Square law modulator. So we have message signal M of t. It is there you will summation. This will be added to your carrier signal, and carrier is simply generated from the oscillator. This is oscillator. So this is C of t. That's equal to AC. C of t is equal to AC cos of twice pi fct or omega ct. This carrier signal, and this will be added with m of t. Then output will be called as v1 of t. v1 of t. This is the output from the summer, and this will be input for the square law device. We'll see what this is. Square law device, right? Then square law device, if you will tell me, give me the example, you have diode is an example of this. We'll try to analyze this a little bit. Then output of this square law device will be V2T. So then this will be passed to band pass filter. Band pass filter. It's not low pass, it's not high pass, it's band pass. Band pass filter, it just pass a band of frequencies f1 to f2 range of frequencies that will be passed through it. It's between two frequencies. That means this is a band of frequency that will pass by this band pass filter. So it depends upon f1 value, and f2 depends upon its range. So ultimately you will get your value, that's SAMT, that's your amplitude modulated signal. Okay, are you drawing this diagram on your notebook?
Yes, sir.
Okay,
Yes.
so this is your square law modulator. Suppose before going for the further analysis, few points that are very important for this analysis. Uh, this suppose this is a graph. This is your input voltage. Just remember this output. Okay, so between these two, if graph will be like this, then you will say that output will be directly proportional to input, and it's equal to some constant k, that is the slope of this signal, this signal graph is K, that's constant, and this graph will be called as linear graph then. Linear graph, right? So this will be a linear. Someone, if this will be like this graph as drawn here, this will be your input x-axis, this will be on the y-axis you have output, then you will see this type of characteristic, signal characteristic are called as scalar characteristics. Scalar characteristics, right? Done?
Yes, sir.
Somebody respond. Okay, so v output in this case will be, because in this case v output is equal to constant, that's equal to slope into vi, that's always equal to k into vi plus 0, because y-intercept here is 0, so you will have equation v kvi, and this k is always slope of this graph, and this is a linear graph, equation for the linear graph. What about scalar? Where do you have the scalar characteristics? You will be having output is always equal to a1 v1 plus a2 v2 square plus a3 v3 cube plus dash 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 dash. This will be output characteristics of a scalar device. In each scalar device, you will have the output like this. So it depending on upon constants here, E1, A2, A3, they are all constants. Depending upon the constant power of VI, that means this is input VI is here 1, I value here is 2, I value here is 3. So depending upon the constant, power of Vi may extend up to 50 or 100. So it depends. Usually you can have is just the approximate range of Vi, approximate power of Vi. It can be power of Vi. It may be from 50 to 100, and that too it depends on the constants. That too it depends on constants. Constant like A1, A2, A3, dash dash dash. And these constants are called as scalar constants. A1, A2, A3, they're called as scalar constants. Done? I hope everything is clear till
Yes, sir.
now. Now, before going further, I will draw the diode characteristics. Everybody knows, you have studied, I hope, in electronics, basic electron. You have practical diode characteristics. Why this is needed? Because scalar device here, it will be a diode. Diode is scalar device. So we'll see which portion of diode will be treated, of the characteristic will be treated as scalar. Because there will be, you just write down, then I will tell you. Characteristics, it will be like this. You have this x-axis, this is your voltage value, this will be your current value, and then equation will be something like this. This will be your diode cut in voltage, after which it will be turned on. Depending upon the value, it is maybe 0.7 volts in case of silicon. No need to remember all these things. What I am saying here, that from 0 to Vi, this characteristics is following the scalar. And after that, this will be your linear portion. And this will be your, after this will be your, after V gamma, that's cut in voltage, this portion will be your linear. Right? Are you getting me?
Yes, sir.
Okay. So diode input will be always, so diode you can say input, that is your Vi, V1t, it will be always your M of t, plus C of t. That's input to the diode. Why? Because scalar device. So input V1 of t will be always equal to M of t plus AC cos of twice by FCT. Why I'm saying this input diode, that's V1 of t, is this? Reason being, you can conclude this from here. Are you getting me? I'm saying MT is your signal. It will be added with the oscillator output. That's your carrier signal. After the addition of these two, you will get V1 of t. And V1 of t is input to the scalar device. That means V1 of t is input to diode. And the output you are getting V2 of t. That's what I'm saying here, that V1 of t will be always equal to M of t plus C of t.
Yes.
So V1 of t is your M of t message signal, and CT is AC cos of twice by FCT. That's it. So there are certain important points which you should remember. For all practical purpose message signal, for a practical message signal, the strength will be usually small. Few points to remember before going further. Note, these are very important points. For a practical, message signal, for a practical MT, the strength will be the strength. That means obviously the message signal strength in terms of amplitude, it will be usually small, usually very small. So the local oscillator, since this will be very small in, so the local oscillator that's generating your carrier signal, it should be constructed in such a way, should be constructed such that such that the peak amplitude of carrier signal should be small, because the amplitude or the strength of your practical message signal is very less. So local oscillator should be constructed in such a way that your amplitude of carrier signal should be very small, so that, what's the reason for this? So that so that peak amplitude of V1 of t, so that peak amplitude of V1 of t will be of the same order as that of your carrier signal, will be in the order of the diode, will be in the order of, so that will be in the order of V cut in voltage of the diode. And because of this reason, it will exhibit the scalar characteristics, and hence it will exhibit scalar characteristics, scalar characteristics. Are you getting me? That means the
Yes, sir.
strength of message signal, that means in terms of amplitude, it's very small. For a local oscillator to match it, you should construct the local oscillator ultimately which generates your carrier signal. It should be of the same value, so that the peak amplitude of V1 of t, that means V1 of t is that MT plus carrier signal, will be of the order of V gamma, because if it will be greater than V gamma, then it will follow the linear portion. And we require this to be in a square law, because it will be passed to a square law device and follow the characteristic of square law. So that's one point you should remember here. Very important point. Getting me? Okay.
Yes, sir.
Anybody having any question? I'm saying that its peak amplitude should fall in this range below this V gamma. So for that, its strength should be very less. That means message signal strength and peak amplitude of carrier, it should match, and they should be less than this, so that it will fall in the scalar characteristics. That's why it will be going, it will act as an input to the scalar device. Okay. Done?
Yes, sir.
Okay. So you have here, you're going further. So you have m of t, you have message signal. It's after converting this to its Fourier transform, you will get the spectrum of this. Suppose its spectrum will look like this. So this will be your omega, this will be minus omega, and this will be 0, and this is your f. Let this omega or f be equal to 1 kilohertz, 1 kilohertz. So similarly, this will be minus 1 kilohertz. And this will be your m of f, right? So carrier, you are assuming here it's equal to 1 megahertz. Obviously, message signal frequency is 1 kilohertz. Carrier is very high compared to the message signal, highest component of the message signal. That means this will be equal to 1000 kilohertz, right? So this in terms of this is 1000 kilohertz. So you can draw the comparison that this highest component in the case of message signal is 1 kilohertz. In this case, it's 1000 kilohertz, which concludes that carrier signal frequency is very high compared to your message signal. So finally, when you will get SAMT, you will see that you will be having the graph like this. And this will be your minus FC. This portion will be your FC, right? This will be FC plus omega. This one point will be FC minus omega. This your minus FC plus omega, and this minus FC minus omega. And you have one here. This will be our carrier here. And in terms of this value FC, this is 1000 kilohertz, right? And this value will be after adding 1000 plus 1 kilohertz, so you'll get 1001 kilohertz. This is this value, this FC value, and this value will be 999 kilohertz. Similarly, this value will be minus 1 kilohertz, minus 1, minus 1000, minus 1000 kilohertz, and this value will be minus 999 kilohertz. And similarly, this will be minus 1001 kilohertz. This will be your final value, which you will get. Now, since we're done with this V1 of t, and V1 of t is input to SLD, that's square law device, V1 of t, we're done with this. So this will be an input to scalar device, and we will get V2t. That means output of SLD device is V2t. So we have V1 of t, we're already done with this. So V1 of t will be your MT plus your addition of carrier. After adding these two, you will get MT is your message signal plus AC cos of twice by FCT. Now this is an input to SLD device. So output of SLD device that will be equal to V2 of T is equal to, we have already calculated this scalar characteristic from the scalar characteristic that output in this case will be A1. So this will be A1 V1 of T plus A2 V1 square of T plus A3 V1 cube of T plus dash 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 dash. Now put the value of equation first in equation second. What you will get? You will get V2 of T is equal to A1. And what's the value of V1 of T? It's given here. Put this value in this equation. What you will get? A1, this is M of t plus AC cos of twice by FCT. Done. Similarly, plus A2 into V1 square. You just square this, put the value of V1 of t, then square this. What you will get is A plus B ka whole square. It will be A square plus B square plus 2AB. Then you will get the final value as M square of t plus AC square cos square 2 pi FCT. Then 2AB twice AC M of t into cos of twice by FCT plus dash dash dash. So these are the values. Similarly, you will put A3 value here, then A plus B ka whole cube. Then you will do, there will be some few terms here. Done. Now this will be your V2 of t, right? Getting my
Yes, sir.
point or not? So this
Yes,
is
sir.
your V2 of t. Now this V2 of t will be passed through a band pass filter. And we have already seen in the spectrum, it will pass the frequencies from Fc minus omega to Fc plus omega. These are the range of frequencies passed by this band pass filter. Similarly here, minus Fc minus omega to minus Fc plus omega. These are the range of frequency because negative frequency don't have any significance. It's just for the sake of symmetry purpose. So it will be passing frequencies from Fc minus omega to Fc plus omega. And omega is the highest frequency component in case of message signal, right? Done?
Yes, sir.
Everybody? Okay. So we will, 1 minute, I will show this. So you will see which frequency components will be passed or not. Since M of t frequency, since M t it's having the highest frequency of omega, and if you will see here, omega is very small. Omega is 1 kilohertz. 1 kilohertz will be somewhere here. Wait a minute. Wait a minute. Okay. Okay. Are you getting me? Are you getting me?
Yes, sir.
Yes, sir.
Do respond. Okay. So I'm saying that V2 of t, it will be passed through band pass filter, and band pass will pass only a range of frequencies. So we will just see before giving the output of band pass filter, you will suppose this is your band pass filter. It will pass frequencies from this range to this, and here in this case, it will pass frequencies from Fc minus omega to Fc plus omega. That means this value already calculated. This is 999 kilohertz, and this value is your 101 kilohertz. Similarly, this will be your minus Fc minus omega, and this minus Fc plus omega, and it will pass the frequencies from minus 1001 kilohertz to minus 999 kilohertz. These are the range of frequencies that will be passed by band pass filter. So you concentrate on this positive value. Now we will try to analyze this value. So this is your M of t. What is the frequency of M of t? Highest frequency 1 kilohertz. We have seen, right?
Yes, sir.
Okay, so this will not be passed by band pass filter because band pass range is from 999K to 1001K. So this will be rejected by band pass. Are you getting this point?
Yes, sir.
Okay. Similarly, this will be FC value. Its value is what? 1000 kilohertz, and 1000 kilohertz is here. So this will be passed by the band pass. Similarly, M square T, it will not be passed by the band pass filter. right? And you can do this because this is equal to a square t. You can take common 1 plus cos twice into 2 fct and divide by 2, and you have here frequency that's equal to 2 fc, 2 into fc, and fc frequency is 1000 kilohertz. 1000 into 2 is 2000 kilohertz, and that's not in this range. Similarly, this will not be passed by the band pass filter. Are you getting my point or not? Hear what I'm saying?
Yes.
Okay,
Yes, sir.
okay, good. Similarly, this will be passed by the, because highest frequency is fc in this case, and this will be passed. So in general, you will say band pass filter output, band pass filter output here will be equal to, it will be equal to SAMT, that's your amplitude modulated signal, and that will be equal to A1, this A1 multiplied by this signal. So you will be A1 AC cos of twice by FCT, right? And this will not be passed, this will not be passed, this one will be passed, plus A2 into 2 AC MC MT into cos of twice by FCT. Now you take common few values, you want A1 and AC is common, then what you will get? You will get 1 plus twice A2 divided by A1, and you also take common cos of cos, and this is empty here, this is M of T, and this is cos of twice by FCT. This is your final value of, and now after some rearrangement, you will get SAMT is equal to A1 AC. Let this be AC bar. That means AC bar is equal to A1 AC. Then 1 plus twice A1 A2 divided by A1. Let that be equal to KA, amplitude sensitivity, MT. And this is your cos of twice by FC. And this is nothing but your amplitude modulated signal, amplitude modulated signal, right? Have you seen this? Yeah. So AC bar
Yes.
is equal to this, and KA is equal to twice A2 divided by A1, and this is equal to your amplitude sensitivity that we have already studied. Done?
Yes, sir.
So we are generally we're concerned with the frequency components. We're not concerned with the amplitude. Someone will say why this should be AC. No, AC bar is just some AC multiplied by constant E1. And this is not a complex constant, real constant, right? So you will get some other amplitude value. You're mostly concerned with the frequency, desired frequency component that you should get. Ultimately, you're getting that at the output. And this is one of the methods by which you can generate your EM signal, and this method is called as square law modulation method, or square law modulator you have by which you are generating this. Or you can say this is square law modulation method. Done? Anybody having any question? Please tell me.
No, sir.
Anybody else?